In this highlight video, we're going to talk about naming alkenes. After watching this video, you will be able to properly construct IUPAC names for alkenes, including what we call E and Z isomers. So these will be stereoisomers. You'll also be able to draw structures from given names. We name alkenes following many of the same rules that we've already learned about naming. For example, we name the longest chain of carbons as the parent, and we want to make sure in this case that that chain includes the functional group. So it includes the double bond. We're going to use ENE, like in alkene, to indicate the presence of the functional group. We then number the chain from the end, giving us the first carbon of the alkene the lowest possible number. We only have to give a number for one of the two double bond carbons. We then name the substituents. We write the name just like we've done before, listing those substituents in alphabetical order in front of the parent, giving the appropriate position numbers. So let's just look at a couple of simple examples here. So we want to find the longest chain that includes the alkene. So in this one, we could just pick this parent right here. We number the chain to give the alkene the lowest possible number. The alkene has higher priority than most of the other groups that we've learned so far. So we're going to say 1, 2, 3, 4, 5, 6. So we have a chloro at 5, we have a methyl at 2, and it's a hexene. So the way we're going to do this, we list chloro first. So this is 5 chloro, 2 methyl, and then we have hexene, but we'll go hex. And here's where we put the number for the position of the double bond. We only list the first number, so 2 in this case. So hex 2 ene. All right, let's look at the next example. So in this case, the longest chain isn't the one that goes straight across, right? We need to include this alkene. So the longest chain is going to go up this way. We number this to give that alkene the lowest possible number. So we're going to number here 1, 2, 3, 4, 5, 6, 7. So this will be a heptene. We have an ethyl group at 2, a methyl group at 5. So we have 2 ethyl, 5 methyl, 7 carbons, hept, 1 ene. It tells us the double bond is right at that very first carbon. All right, so most of this just follows what we've done before. Let's do a few more examples. This first one should be pretty easy, right? So we can pick this chain right here, number it to give the double bond the lowest number, so we're going to number it from left to right. That gives us another hept 2 ene. We have our methyl group at 2 and a methoxy group at 5. So 5 methoxy, 2 methyl, hept 2 ene. Now the next one has 2 double bonds, right? So we could pick a chain here, and when we have 2 double bonds, this is going to be called a diene. And so we're going to name this as a alkadiene. So the alka part, let's see how many carbons we have. 2, 3, 4, 5, 6. So this is going to be a hexa. We've got to give our numbers 1, the beginning numbers of each of the double bonds, 1, 3, diene. All right, and we have only one substituent. We have an ethyl group at position 4, so 4 ethyl hex 1. Oh, this should be hexa 1, 3 diene. When we name cycloalkenes, the double bond will always be between positions 1 and 2 if the double bond is the highest priority group. So it'll be 1, 2, and then we put the first substituent at the lowest possible number. For example, on this first one, because we want the methyl group to get the lowest possible number, we're going to number it here 1, 2 across the double bond, and this will be at 3. So this is 3 methyl. Because the double bond always starts at 1, we don't have to put a number for the position of the double bond. So this will be 3 methyl cyclohexene. All right, so what about the next one? We have a cyclopentene, so where should we start our numbering? All right, we want to give the first substituent the lowest possible number. So we're going to start numbering right here and go this way because that puts that methyl group at position 1. So we have 5 chloro, 1 methyl cyclopentene. All right, everybody see how to do that? Now we can have geometric or stereoisomers when we have alkenes. So a common situation, let's add in the 2 groups on the double bond that aren't being shown, is that we have an carbon chain that has an internal double bond. Okay, and so in this case what we would do is we look at an axis down the double bond and we look at the 2 biggest groups. So we have a propyl group here and an ethyl group here, and we see that these groups are on opposite sides of that dashed line, or opposite sides of the double bond. Okay, so they're going to be on opposite, and so we call this, just like we did with rings, this is called trans. So this molecule would be trans hept 3-ene. All right? Trans tells us what stereoisomer we have versus, remember, if we have them on the same side, it would be cis. But what do we do when we have a molecule like this one on the right that has 4 different groups attached to the double bond? Right? Which groups would be cis? Which would be trans? So this is a much more challenging situation. So what we're going to do is we're going to jettison this cis and trans terminology, and we're going to go to something that's called EZ. Designation. All right, and this system uses a priority ranking system similar to what we did when we were determining chirality of stereogenic centers. Okay, so R and S. How this system works is that on each end of the double bond we're going to have 2 different groups, and we're going to rank those 2 groups. So if on this end we rank 1 as being high and 1 as being low, all right, so these are ranked to each other. And then on the other side, we might have this one ranked high and this one ranked low. So then what we do, just like we did for the trans, we're going to draw a line down the axis of that double bond, and we're going to look at the two high-ranking groups. So high and high, and we see that these are on the same side. All right, and so this arrangement is going to be called Z. Z actually stands for Zusammen, which is a German word, but some people have found it easier to remember if we just say that these groups are on the same side. The same side. Right? That's one way to remember that. All right, so the other possibility is here's our two groups, and we have a high-ranking group here, low over here. But in this case, we have the high over here and low. All right, so now we have those. We look at the axis down the double bond. We see that the high group and the high group, these are on opposite sides. And opposite is referred to as E. Let's look at a few examples here. So the first thing that we need to do to determine E or Z is we have to decide whether there is a double bond in the molecule that would have possible stereoisomers. And what it takes for a molecule to have an alkene to have stereoisomers is that each end of the double bond has to have two different groups attached. All right, so let's look at this first molecule in the upper left. So what about the double bond on the right? Would this double bond have stereoisomers? Well, we can see that on this end of the double bond we have this ketone, and on this side we have this double bond. These two are clearly different from one another, and so we could rank one high and one as low. But if we look at the other side of the double bond, this has an ethyl group, this has an ethyl group, so these two are the same. So if we swap those two, switch places, we get the same molecule back. And so this double bond does not have stereoisomers. What about the other double bond? All right, we see a methyl, we see a CH2 with a bromine, here we have an H, and here we have this big group. So yes, this double bond will have stereoisomers. So we have to rank the groups. So one thing we should always do is make sure that there's some atom drawn at each of those positions. So we're going to compare these two, right? We have a CH3 here, CH2 with a bromine. So bromine is directly attached to the first carbon. That's going to give it a higher ranking. So this is going to be high, and this is going to be low. We don't rank them 1, 2, 3, 4 like we did for stereogenic centers. Now for the second carbon, okay, that's this carbon right here, we have a hydrogen and we have all this big group over here. So the big group here is going to be high. Hydrogen, lowly hydrogen is always low. So then we draw the line down the axis of the double bond, and we see that the two high-ranking groups are on opposite sides. All right, so opposite. So this equals E. All right, what about the one in the upper right? Are there any double bonds in that molecule that would have stereoisomers? All right, what about this one out here? Okay, that would not, because there are two hydrogens here, right? So those two hydrogens are the same. If we switch places, we get the same molecule back. These two groups are clearly different. We can't have a stereoisomer in a benzene ring, and these two groups are different. Okay, so yes, we can have a stereoisomer or set of stereoisomers around that middle double bond. So when we rank them, remember that if we have a carbon with a multiple bond, like this carbon with a double bond, we treat it as being bonded to two carbons. So if we do what we did before, this one would be attached to a carbon, and a hydrogen, right? The hydrogen is right here. This carbon here has no hydrogens, it's only attached to carbons then. So then we compare those two. We have carbon and carbon, tie, carbon, carbon, tie, hydrogen, carbon, and so this one over here gets the high, and this is low. All right, what if we look at the right end of the double bond? We have this carbon here is just attached to 3 fluorines. This one over here is attached to a bromine, a carbon, and a hydrogen. So we compare those two. First atom, because we've listed them in descending atomic number. Bromine versus fluorine. Bromine has a higher atomic number, so this is high, this is low. So again, we draw the line down the middle. The high groups are on opposite sides, so this molecule is E as well. All right, let's just do the one on the lower left. Okay, one double bond. The groups on each end of the double bond are different from one another. This isopropyl here would be ranked higher than this ethyl group. Right? The methyl group would be ranked lower than this CH2 with another carbon, so this is high, and this is low. Two high groups are on the same side, on the same side, and so this is Z. So let's go ahead and name this molecule. If it doesn't get too messy, let's see. Here's the longest parent. All right, so what do we have? We're going to start numbering over here. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be an oct-3-ene. And then we have methyl, ethyl, methyl, bromine. Okay, so we're going to start with the bromine. 6-bromo. Next in the alphabet, ethyl. 3-ethyl. And then we have two different methyl groups. We have one at 2 and one at 4. So 2,4-dimethyl. And then we have the oct-3-ene. All right, so there's the whole name. The one thing we've left out is that this is a Z double bond, and so that goes in parentheses out in front. Z. So Z, 6-bromo, 3-ethyl, 2,4-dimethyl, oct-3-ene. All right, I'll leave that bottom right one for you to work out on your own.